going through the attack lab. The first thing you need to do for the attack lab is go to the CS2400 applied Siesta Colorado Edu server, and from there the link will be in the assignment. The attack lab server, go to that link at the bottom. You will then be asked to provide your name and email address. This is used to tag the binary that you're going to get. Just enter in your identity key and your email address. When you then submit this, you will get a target file. The target file includes information that you're going to need and take over to the either your Linux system or to the hub environment. You can download multiple target files, but you should really only work and submit one of them and identify which one it is in your uploads. It'll take a few seconds or maybe a minute to produce the target file because it needs to be compiled and prepared for you. I've already downloaded a specific target file, so that's what I'm going to start working on now. Let's take an overview first of what the attack lab is going to be doing. The basic goal here is to do a code injection attack, and we're going to be targeting a buffer overflow in a routine getBuff. getBuff is going to have a buffer of a certain size, and we then need to do a we're going to input information that's going to overflow that buffer. What we're going to do right now is show you the steps of unpacking the library, the use of some different tools that you'll need to be able to do your application. So I've already downloaded the my target file. So here's my someplace, target 7. So I'm going to go ahead and create a terminal session. I can do an ls and see my files, and I need to do a tar xvf, that means extract verbose, and from file target7.tar. I'm using tab completion to complete the commands. That pulls out these commands here, or these files, which are now in the target7 directory. I'm going to navigate to that directory here, and then from here I also have to go to that same directory. There are two binaries, ctarget and rtarget. They're for the two different phases of the program, or of the lab that you need to do. In each case, we're going to create a disassembly of each file because we're going to be able to refer to it. So I'm going to do an objdump -s of ctarget and have that output go into ctarget.s. I'm going to do the same thing for rtarget. Now let's take a look at ctarget.s. Oh, I was saying .s when I should have said -d. So -s just prints out the section's information. What I want is the disassembly. So this now shows the disassembly of the program overall. There's lots of pieces in here. Fortunately, we'll be able to search for it. Let's go back to our PDF description. So basically, this there's a routine test, and that routine test is going to call this getBuff routine. The getBuff routine is the one with the buffer overflow attack. So this is getBuff here. There's this buffer of a specific size that's listed here, and then it does a call to getS, which gets a string from the standard input, and then it returns 1. The task in this lab, as they described in the write-up, is that we need to provide a string that overwrites the return address such that we can call the target1 routine. So when we normally call getBuff, when we return from that, the default return would be to say no exploit getBuff returned and then a value. What we want to do is to modify this, or to have the string be such that we modify the stack such that touch1 is called. Let's take a look at these different parts. So we're going to look at test, touch1, and getBuff. So I'm going to search for getBuff. Here is the getBuff routine. Touch1 is right next to it. The getBuff routine is this that's been highlighted here. The steps are going to be fairly similar on yours. There's going to be a subtraction of some amount of stack space here allocated for that's basically allocating space for the buffer. The pointer to the top of that, the lowest address in memory, is passed into RDI, which is the first argument register. We then call getS, which will then write the data into that location. Then there is the move of 1 into EAX, so that's going to be the return of 1, and then it's going to deallocate the stack frame and then return to the caller. Touch1, the main thing that you're going to need to know here is the address of touch1. So this is the address, the full 64-bit program counter address of touch1. Likewise, you'll need to know that for touch2 and the other ones as well. The routine test should be down here. And in this case, what test does is, again, it allocates some stack space. It calls the getBuff routine that we had above, and it more or less does exactly what the C code says that it should do. The one thing we're going to note here is that what the address here right after the call to getBuff is. So in my particular binary, that's at address hexadecimal 401945. We're going to start now with ctarget. So if I just run ctarget and give it something, it asks me for a string and it says no exploit. If I run it with a much longer exploit string, we overwrite the stack and we get a segmentation fault. What we're supposed to do in this assignment is provide a specific string that's going to overwrite the stack in a certain way. First thing we're going to do is take a look at ctarget. I'm going to always display the program counter. I'm going to set a breakpoint for getBuff, and I'm going to run the program. Alright, so I am now in getBuff, and if I look at the next 10 program instructions, I see here that I'm at the point where I'm about to subtract the stack pointer. I'm going to move the stack pointer and call getS. So what I want to do is I want to wait until the stack pointer's been subtracted. So I went to the next instruction, did an SI. I'm going to now print out the stack pointer as a hexadecimal address. So that's the current top of stack. I'm going to use NI because I don't want to go into the getS instruction. So I'm going to step to the instruction immediately following this. And I'm going to enter a string here that will be easily recognizable. So I'm just going to say, how now, brown cow. I'm now at the instruction immediately following the getS. The getS call place the string in the buffer that is at the top of the stack. So if I examine that part of memory as a string, I will see the string that I entered. If I look at it as a sequence of characters, I will see the string that I entered and then the null terminator right there. And then there's some other stuff after this. Now let's take a look at this not as a string, but as a series of instructions. I don't expect these to make any sense. But if I was to execute that string, I would execute a push instruction, I would do an out instruction, which would cause an exception. Some various other things would happen. Some bad instruction would occur here, so on and so forth. So all I'm doing here is I'm looking at the stack as strings, as bytes, characters, and as instructions. So understanding this is that the data in the stack can be any of these things, as how I look at it. is important, because what we're going to eventually do is we're going to be executing code somewhere in this set of code here. And we're going to be doing it through injecting a string that, when interpreted as an instruction sequence, will actually be a useful program. For now, what I'm going to do is I'm going to look at this as a long hexadecimal. Sorry, as a word hexadecimal. So these are 32-byte quantities. One of the things I want you to note here is, so there's a portion of the buffer that corresponds to hexadecimal 28 bytes or whatever it was that my version of getBuff actually allocated. And then down here, there's an address that looks suspiciously like the return address of the into get test. So in other words, if I looked at 10 instructions at the routine test, I see that this instruction, which is immediately after the call to getBuff, has address hexadecimal 401945. That's the same as this address right here. If I rerun this program, I would see that this is the top of stack when I enter getBuff. That's the return address. So if I enter a string that is appropriately long enough that it can overwrite this string here, then I can cause the call to getBuff to return to a different destination address. So that's more or less the first phase of the RTarget program that you need to do. Is you're going to basically overwrite that, you're going to put in some string, and you're going to modify the return address to go to the touch 1 routine. Level 2 and 3 become slightly more complicated. You're going to then be injecting code into the buffer that you then need to execute. Let's take a look at how some of the tools provided with our lab. So one program that is provided is hex2raw. I have a couple of sample strings or sample files that I've produced that I'm going to take a look at. So these files are sample assembly and sample hex bytes. So I'm going to copy those from above. And we're going to use that to figure out how to use the hex2raw program. So let's take a look at the sample hex bytes. So sample hex bytes, I can actually also look at it in the file browser. So sample hex bytes is a series of series of bytes that are with spaces between them and optional comments at the end. These bytes are each 2 hexadecimal digit number here is going to be a separate byte in the data. What the hex bytes program does is it translates this human readable ASCII representation of this file into a file that actually has these bytes. So in other words, in this case, each of these bytes is 2 ASCII characters. So the highlighted number 48 here is actually 16 bits of data, 2 8-bit bytes, the first of which is the ASCII character 4, and the second of which is the ASCII character 8. When this is translated, there will be a single byte which will have the hexadecimal value 48. That may or may not be able to be represented by an ASCII character. Let's take a look at a program that helps us understand this decoding. So the program is called OD, which originally stood for octal dump, but that's not what we're going to do. We're going to use octal dump to look first at the sample hex bytes file. Octal dump just prints things out, in this case, hexadecimal. And so these are the first set of characters, and I'm going to actually print it out first as characters. This is the output, or that file with individual characters being printed out by the octal dump program. And I can print it out as individual individual bytes. I'm trying to remember how to print it out just single byte at a time, but we'll just wing it with this. So this is the string 48. The 20 is a space. The 63 is the letter C. So the 48, these are in little endian order, and I'm looking at it as 16-byte items. So I would need to figure out how to see it as truly hex or single byte hex numbers, but I don't remember the exact syntax to be able to do that. But what I want you to understand here is this file actually contains ASCII characters representing the numbers 48. So now if we run hex bytes or hex2 raw, and we're going to take as input the sample hex bytes and output it as sample hex bytes dot data, and now we're going to octal dump that sample hex bytes dot data. In this case, we've now translated the ASCII representation of these numbers, the human readable version, into an actual ASCII character. So in other words, or not ASCII character, but hexadecimal bytes. So in other words, the first byte of the file here is 48, and the second byte of the file is C7. That's exactly what we had written, what we wanted. So in other words, we wanted a 48 followed by a C7. But this is written in ASCII, and it includes this comment, and it's quite long. The sample hexbytes.dat file actually includes precisely each byte being what we had written in the multiple characters in our text file. If we were to just look at this file, so as characters, we would see that apparently it's something and the capital H, so I think that that's what 48 winds up becoming. C7 isn't representable as a printed character. And these other representations here, these are the octal representations of the different characters that are being printed out here. The 0A at the end of this, that's the new line character. And then there's a null terminator as well. So this is a character string, but it's not a typable character string. That character string represents the input that we had typed in here. So as obviously indicated by the comments here, what you're going to be doing is putting in a hexadecimal encoding of a sequence of instructions that you're going to want to input into the getBuff routine. You're going to then encode it into an actual string or the actual string representation of those characters instead of the ASCII expanded version that we had here. So this will be the actual input string that we would want to place into our program. And then we need to use this as the input to our program. So there's a command argument on the C target program that allows us to do this. So now let's see what this looks like when we're actually running the program C target. So we're going to run our program. We'll set a breakpoint for getBuff. We're going to run the program with the input of sample hexbytes.dat. So we're now at getBuff. If we look at the top of the stack, we see here that this is the return address from the call and test. This is exactly what we'd seen before. So this is the return address to the call and stack at the top of the stack when we enter. Now we've subtracted a value from the stack. Now we're going to make the call to getS, and it's really going to actually read from the file this time. Now we've done the call to getS, and we're about to exit. So let's take a look at now what's at the top of the stack. So I'm going to look at this as hexadecimal values first. These values here, so let's actually take a look at it as bytes. "48, C7, C1, F0, 11. Where have we seen those before? 48, C7, C1, F0, 11. So the data that's on the top of the stack that was typed in came from this sample bytes file, and it's now on the top of the stack as the actual bytes, not the ASCII string. And if I was to look at the top of the stack as an instruction, I would see that it is a move instruction to RCX. In other words, it's what I was trying to encode and have be placed on the top of the stack. So let's review where we are with this. We have a file, sample hex byte, which allows me to edit and use a text editor to enter a series of hexadecimal digits. Then we have the program hex2raw that will take the coded file, the ASCII file, and produce an actual file of bytes. So it takes the ASCII file and it produces an actual file of bytes as opposed to the ASCII representation of those hexadecimal values. That string is not typable, so I have a way of passing it in when I run my C-target program. And if I take that file as input, when I'm done getting the call to getBuffS, I actually have an instruction on the top of the stack. I could also look at the top of the stack as a string, and it's that untypable string that I had seen before. I can also look at it as just some data, and I see that it's my string, and if I go far enough, I see that it's my string and that there's a return address here that's of interest to me. So if I had entered a long enough string, I could overwrite that return address with something meaningful to me. So that's what the hex2raw program does. Now let's take a look at how do I actually define what the contents of this would be. So assume that I have some sort of an attack string that I want to be able to put into place. So how do I figure out what those bytes should be? Let's take a look at our sample assembly file. This is straight out of the homework assignment. So in this case, I have a sequence of instructions that I want to be able to find out what their binary hexadecimal representation would be. So I have sampleassembly.s. So I'm just going to do cc-s, sampleassembly.s. cc-c. So I now have a file sampleassembly.o, and I can obj dump that. This is the code that I had entered into my sample assembly file, and these are the bytes over here that would correspond to those instructions. So I could copy these bytes into, for example, my sample hex bytes file. And maybe what I'll do is I'll just copy all of this. Get rid of the leading parts here. Put this in comments. So now I have a file that has the bytes that represent the instructions on the right-hand side. And then I can run that through hex to raw. And if I now look at this as hexadecimal data, I have the instructions here. This is now a file that represents a string that is likely unprintable, but it corresponds to this sequence of instructions. This is the process that you're going to use to actually inject code onto the top of the stack. You're going to write your exploit string in an assembly file. You're going to then, like this, you're then going to use the assembler to get the appropriate hexadecimal representation of these instructions. You're going to put that into a file that you then run through hex to raw, and that's going to produce a string that is likely untypable, but which you can then pass into ctarget to do something. So in this case, although I injected instructions into the buffer, I did not cause that buffer to be executed, and so no exploit was done. So now let's take a look at the R-target. So in R-target, we're using what is called return-oriented programming, and in this, we need to find instructions of sequence that are followed by a return instruction, and that return instruction is going to pop an address off of the stack and then execute another gadget, as it's called. The gadgets are in a file, and if we take they're in the binary, the R-target binary, and they are between start farm and somewhere down here end farm. Yeah. So everything in between this are different gadgets, and you'll notice that they're all fairly simple instruction sequences. So they're very small routines, because this is a learning exercise, not a true exploit. But what we're going to do is focus on this one gadget here, addval. So this is somebody has written this as a load effective address with a particular hexadecimal value loading into register EAX. Let's take a look at this and see what this actually looks like when we run it in the binary, to understand how it can be a possible gadget. So we're going to run GDB on R-target. And we're not going to run it at the moment. What we're going to do is first display a program counter, or a single instruction at address addval 453. That's the address of that routine. We'll show three addresses. So here is the instruction that was encoded, followed by a return queue. Now we can make this be something more useful, so it's very rare that we would want to have this specific sequence of instructions in our exploit string. But if I go to the next instruction, well, I see an exchange followed by a bad instruction followed by a no-op. That doesn't look very promising, because this bad instruction would cause the machine to halt, or the program to halt. Let's look at +2. Oh, look, there is a move instruction, RAX to RDI, followed by a no-op, followed by a return queue. A no-op is an instruction that has no actual effect. So this, if I could execute this address here, I would be able to execute a RAX to RDI move, and that's useful because RDI is the first argument register to a function. And then I would do a return, which would pop an address and then execute the next gadget address. So what you're going to need to do is to examine the different gadgets that have been provided to you, and then, just as I was doing here, go through and figure out, are there useful instruction sequences that are here that you could exploit in your exploit string. If you look at the assignment, one of the many long pieces of code in the back is encodings showing the move Q instructions and move long instructions. So in our particular case here, what we were doing was we have a move RAX, RDX. So I'm going to look at this as hexadecimal bytes. And I see here that that instruction is hexadecimal 4889C7. I'm going to guess that the 90 is the no-op and the C3 is the return instruction. If I go back to this table, I see here the a move from source to destination 89C7. And here a move quad is a 4889C7. So that's moving from an RAX to an RDI is this byte sequence, which is exactly the byte sequence that we saw in the binary. And then the no-op is just a no-op in this particular case, and then the return instruction is in fact the C3 for that. So if we're able to then pull out, like in this case, here's another 4889C7 that was encoded apparently as this more complicated move long instruction, but this would have also been a move of RAX to RDI, just as the example that we went through is a move of RAX to RDI. So in this particular case, these are the gadgets, and then you need to determine what is the address that you would return to execute that sequence of instructions. And then you're going to create a long string with those sequence of addresses, and that's going to be what you inject into RTarget. In order to encode those addresses, you're probably going to use the hex to raw program once more. But instead of it putting in strings that would represent code, you're going to be putting in strings that will represent return addresses of gadgets that you wish to execute. But other than that, the use of hex to raw is going to be fairly similar. This lab is challenging. Do the first part first, the C target, and then tackle the R target. The C target, the first one, is pretty straightforward to be able to get to. You don't actually have to execute any code on the stack, so you don't really have to inject code. All you need to do is overwrite the return address. For touch 2, you need to actually put some code into the to the stack, and then you need to call routine touch 2 with a specific argument being passed in. That means that you need to put some data into the register RDI and then cause the code at touch 2 to be executed. And likewise for touch 3, you need to pass in a particular string. All of the data that you're passing in needs to be injected into the stack, and then you need to cause the code to execute the code, or the return out of getBuff to execute the code in your stack. This is a fun assignment because this is the mechanism that people use to exploit computers and break into computer systems. And again, you shouldn't do that, but you should certainly do it in the context of this assignment. The return-oriented programming shows that even if you are able to cause the stack to not be executable, then you can still cause the program to execute arbitrary code by doing this return-oriented methods and finding gadgets. In the RTarget code, you cannot actually do a code injection because the stack is marked as non-executable. Whereas in the C-target, code on the stack can be executed. If you have questions and problems, speak up in the class forum. Most of the tools that you're using here are pretty straightforward, but they take a little while to understand. Often a difficulty that students have is the distinction between the ASCII version of the binary that I'm trying to put in and the raw version of this where it's the actual strings. And it's just the difference between this is a text file and then the other one is not a text file anymore. If I was to cat the sample hex .dat, I don't even see anything because the characters are unprintable, and if I look at it as data as characters, most of these characters are unprintable, and that's why I can't see it necessarily. So that's usually the big stumbling block for people, is the encoding of the strings.